Okay, now let's do one example for the circuit emitter follower configuration. So in this circuit, this is different with what we have discussed or what we have analyzed in the previous video. Now we have the signal here, we have RS and we have the load connected to the output. Okay, so this is the emitter follower configuration, or sometimes we call it common collector. Input at the base and output is at the emitter. Okay, the question is determine the value of impedance, input and output impedance, voltage gain, AVS, and current gain and power gain. So the given here, this is given is the VA is infinity, so means that VA infinity means that the R0 is also infinity. So R0 is infinity. Okay, IC is 2.37 milliampere. From IC we can calculate the GM. GM is 2.37 milli. So this is IC. IC is 2.37 milli over 26 milli. So this is equal 91.15 milli Siemens. So the unit for the transconductance is the capital S Siemens. From GM you can calculate the R pi. R pi is beta 120 over GM. So this is 1.32 kilo ohm. Okay. The first step is you need to redraw the equivalent circuit. So this is the mid-band equivalent circuit. Okay, so see here. So we will not use this equivalent circuit. So you can take some time and then you can redraw it by your own. How this can be how you can get this one. Okay, inside this one for R1 and R2 is in parallel, so we have combined the R1 and R2 as only one resistor here, and R1 and R2 is, so see here R1 is 8.2, R2 is 1.5K, so R1 is 8.2K and 1.5K. So this is using the parallel, you will get this one 1.27. So this is 1.27 kilo ohm. For R pi we have calculated the R pi is 1.32K and the GM is 91.15 millisiemens. Okay, so next we want to calculate the ZI. Okay, the ZI, okay, it's already labeled here. We have the ZI, we have the ZB. ZB is actually the impedance seen from the base. So this is base point. Okay, so you know the ZI. ZI is equal to R1, R2 parallel, and then parallel with the ZB. Okay, how to calculate the ZB? The calculation of ZB. So here the Z, using the Ohm's law, the impedance is equal to voltage. So voltage at the base is VB over the current at the base, which is IB. And then VB is voltage at the R pi plus voltage at the RE. So since at the denominator we have IB, so we need to express the voltage as a function of IB. So the voltage drop at the R pi is IB R pi 1.32K plus voltage drop at the this Okay, so take note that the voltage drop at the RE is equal to voltage drop at the RL, and then since we know the IE here, the IE current is not the current at the RE is not equal to IE, because the IE it will be divided to flow at the RE and to flow at the RL. So what we can do is we can combine the RE and RL and then times with IE. So this is IE RE parallel with RL. So this is IB, then IB. Okay, IE is can be replaced, can be converted into IB using beta plus 1 IB. So this is 120 plus 1 beta plus 1, and then this is IB. RE is 1K, RL is 10K. So RE is 1K, RL is 10K. So this is as a function over the IB. So now IB can be cancelled out. So the calculation, so you get 1.32K plus this is 110. And then you get ZB is 111.32 kilo ohm. Okay, so when you get the ZB, ZI is the R1 parallel with R2 is equal to 1.27 kilo ohm parallel with this is 111.32K. So the answer for this one is ZI is equal to 1.256 kilo ohm. So this is the answer for input impedance. Okay, as for output impedance, so we will see that from in the output impedance, for starter, maybe it's better for you to redraw the circuit in order for you to see the resistor network which can be observed from the output point. Okay, so I can redraw the circuit here. So since the output here, the Z out is seen from this point, so I can plot here something like this. So this is the V out here, and then we have here, this is RE, and then at the collector here, okay, this is emitter. Oh sorry, this is not emitter. Emitter is different. So and then we have here, this is a current source at the collector. So emitter should be here. So emitter terminal of the base should be here. And then we have here, this is R pi, and then the R pi, we have here, this is base. And then for the output impedance calculation, we will assume the Vs to be 0, grounded. So Rs and R1, R2 is in parallel. So this one is, so this is Rs parallel with R1 parallel with R2. Okay, and then the current direction for the base is, this is IB, and the V pi is something like this. Okay, so from here, the in this redraw circuit, the Z out is actually the impedance seen from the V out, the output port, towards the left side. So the Z out is equal to RE parallel with what we call it as a ZE, the impedance seen from the emitter. Okay, the impedance seen from the emitter is voltage at the emitter. So voltage at the emitter part, we can use the R pi and these resistors in parallel, RS, R1 and R2. So you can use this one. So the ZE actually VE over negative IE. Okay, negative IE. Because the IE current is opposite of what you want to calculate. So IE current is towards the right hand side, but here the voltage VE here is pointing to the current supposed to be towards the left side. So that's why we put this at the negative IE. And then the VE here, so the VE here is equal to the voltage drop at the R pi and voltage drop at this resistor. So this can be, you can combine this R pi and this resistor in parallel, and the current flow across this resistor is IB. So here this is minus IB, this is R pi plus RS parallel with R1 parallel with R2. Okay, so upper side we have the as a function of base current, so we can change the IE to base current. So this is this is negative IB beta plus 1. So okay, cancel out the negative IB. So you got this value. Okay, if I put all the value here, so R pi is 1.32K plus RS is 600 and R1 parallel with R2. So this is R2, this one R2 is 1.27K, and then beta plus 1 is 121. So you got the answer is the ZE is equal to, so okay, so ZE is equal to we want 14.3, so equal to 14.3 ohm. Okay, so this is only ZE. So the Z out, you need to for the Z out, so I can use this one. For the Z out is actually the RE with the ZE. So the RE is 1K and ZE is 14.3 ohm. So the answer for this is you can calculate this one. This is 1000 times 14.3 divided by 1000 14.3. So you got this answer is 14.1 ohm. So the Z out is 14.1 ohm. Okay, so you got the output impedance. Okay, so you may notice that the difference between this example and our analysis in our previous analysis. In our previous analysis, we don't have the RS here. We don't have the RS. So in previous analysis, this R1 and R2 disappear because of the bypassing. Okay, now we go to the calculation for the AV. Okay, so what is AV? AV is V out at the load over VI. Okay, so we can I need to redraw this one. Let me redraw the equivalent circuit so we can have a clear view. So this is the okay, let me copy this one. Okay, so the V out is voltage at the RL. Okay, how we can calculate the V out? V out is this combination of RE and RL times the emitter current. This is IE. So IE times RE parallel with RL. So you got this one is IE, RE parallel with RL. I think we have calculate this one. RE parallel with RL is 0.909 K. Okay. So and then what is VI? VI is the voltage at here. Okay, voltage at here. You know VI is equal to VB. This is VI. This is VB. So VI is equal to VB. And then we know that VB is equal to IB ZB. So from this equation, AV is equal to, so IE can be replaced with IB using the beta plus 1. So IE is equal to IB, beta plus 1, 120 plus 1, and then times 0.909 K, and then this is IB. Okay, we already have the value for the ZB. The ZB is 111.32K. So hence IB can be cancelled out and you can get the value of AV. The result is 0.988. So this is the result for the AV. Okay. How about the AVS? So AVS is equal to V out over VS, which is also equal to V out over VI times VI over VS. So V out over VI here is a AV times VI over VS. Okay, so we know the value of AV. So we need to get the ratio between VI and VS. So VI is the voltage division between the amplifier with the signal impedance or signal RS. So the VI is actually a ZI over ZI plus RS VS. So here the ZI, the impedance, we have calculated as 1.256K, and then this is 1256K plus 600. So VS, so lastly we can get VI over VS is equal to 0.677. Okay, from this you can get the AVS is equal to 0.988 times 0.677. So this is equal 0.67. So this is the answer for AVS. Okay. So and then if you want to calculate what is the current, so we can calculate the current gain. Okay, let's calculate the current gain. Okay, if you want to calculate the current gain, let's say AI. So I define AI as the IL over II. So IL is the current at the load. This is IL, and then I in is at the current at the input port. Okay, so the current at the gate at the IL can be we can use the current divider to relate the IL with the IE emitter current. So IL is equal to RE over RE plus RL times IE. So IE is 1K. This is 1K plus 10K, and then IE. IE. And then you know that IE can be replaced with IB. So this is 1k over 1k plus 10k, and then times with 120 plus 1. Now it's become IB. Okay, so this is our first equation. And then what is II? So II, you can use the relationship between II and IB. So IB is a current division between the ZB and the R1 parallel with R2. So IB is equal to R1 parallel with R2 over R1 parallel with R2, and then plus ZB times II. So from this equation, this relationship, you can get II is equal to R1 parallel with R2 is equal to R1 parallel with R2 is equal to 1.27, and then this is plus the ZB. ZB is 111.32k, and then this one is 1.27k. So you got this one, second equation. So from 1 and 2, you can get the AI. AI is 1k plus 10k, 121 IB, and then you got here 1.27k plus 111.32k over 1.27k IB. So IB can be cancelled out. Lastly, and then you will get the this one is AI is equal to 0.1. So I can calculate this one. So 0.1 something. If I'm not mistaken, 0.1224. Okay, so this is the AI. Okay, once you get the AI, you can calculate the power gain. Power gain is AV times AI. So AV is 0.988 times 0.124. So the AP is, the power gain is, so you got here is 0.12. So this is the final answer.